So yeah, thank you for the opportunity to let me speak about autonomous unmanned airships. This is a topic which is very close to my heart because I spent about 5.5, 6 years working on this for my PhD. So yeah, here it is. So this is the brief outline of my talk today. So I'm going to give you a little bit of background about what airships are, what are the issues with airships, and then I'll also talk about the mitigation of some wind effects, and then finally we'll get into autonomous control. So to just to give you a background, airships are these kind of vehicles. So these are on the screen. What you see are contemporary airships. They come in variety of ships, although the popular one is probably the first one that you see. But in the present time, you have a lot of different variations. So you have multi-lobe, which is the one written with buoyant. Then you have a lenticular shape, which is the orange one. And on the top right-hand side, you have a hybrid aerostat vehicle. So you have a variety of designs and configuration now for airships. Now, airships are those vehicles which derive majority of their lift from buoyancy. So typically, these airships they have a gas chamber or an envelope which basically contains a lighter than air gas, and that is the main source of lift generation. So this airships have more in common with submarines as compared to unmanned aerial vehicles or even aircraft. So that's the key difference between that. Now, why do we have to look at airships? To understand that, let's have a look of the qualitative analysis of various three different kinds of vehicles. So you have multi-rotor or rotorcrafts, then you have fixed wing, and then you have airships. Now, if you look at this, there is the parameter. The comparison is done across variety of parameters. So the first and foremost that is of importance is endurance, range, and payload capacity. So you clearly note that airships have a very high capacity in all of these three. This is mainly because you don't have to expend any energy in staying afloat in the air. The lift generation happens free of cost because of the lifting gases. Although the speeds are low, they can still be as quick as multirotors. Performance wise, they are very highly efficient. Safety is even enhanced. Now, this is because even let's say there is some kind of a propulsion failure when an airship is flying. The airship is not going to come down crashing like a multirotor or a fixed wing. It's going to gradually descend like a balloon in the air. So probably, let's say maybe a pilot is flying an airship and there is some kind of a propulsion failure, it would probably take him about half an hour to crash. So that's how slowly the airship would descend. The noise levels are very low. So multi-rotors, as you know, they produce a very high-pitched noise, and it is around I think 80 decibels, which is equivalent to a very busy day in the traffic. Fixed wing also produce a lot of noise. On the other hand, airships do not produce noise because they don't have to depend on their propulsion system again to stay afloat in the air. Radar signature and IR signature are both low for an airship. Now, this is because of the low density material and uh, materials which basically have very low signatures. That's the kind of material that are used in airships in their construction. Setup time is slightly higher because this would require you to fill helium into the envelopes. The cost is comparable and sometimes even lower as compared to fixed wing or multi-rotors. And of course, the size, as you might have guessed, is larger than the conventional one. So there are several use cases where size doesn't matter or even the setup time does not matter. And that is where it is ideal to use airships. Things like surveillance, which require 24 by 7 persistent operation and maybe a long uh, uh, delivery of goods in a very long distance. So those are the kind of things that airships can do much better compared to their heavier than air counterparts. Now, historically, if we look at the accidents that have happened on airships, so there are 83 up to date. And out of this, you see that the majority has happened because of lifting gas related. Now, I would like to tell you that this was in the early eras of airship before 1950s, and because this was mainly because hydrogen was used at that time. Now that problem has been addressed by the use of helium. So it's typically helium that is mostly used in airships this day. So lifting gas related problems, you can say, more or less has been addressed. But what remains is the problem of instability in bad weather and the loss of control of airships. In short, it is very difficult to maneuver an airship, especially when there is wind disturbances. So that is the key problem right now in the widespread use of airships. So let's understand why that is the case. So as I mentioned, the airships and wind, they don't see eye to eye. They basically, if it is windy, it is often deemed unfavorable for airship operations. So why is that? So on a conventional aircraft, let's say any aircraft you consider commercial airliner, they would have this weathercock stability, which is basically like what we see in a weather vane, that it would align itself in the direction of the wind and face the wind head on. That's what we desire if it has to be weathercock stable. So this is what happens in a conventional aircraft. It would align itself in the direction of the wind. Now you see that it is facing the wind with the full might of its engine. So it's kind of easy for the aircraft to overcome this drag from the crosswinds. But in case of airships, they don't do that. They actually go away from this. So that's the reason why it is unstable. Now look at why exactly again it is directionally unstable. Now, if you look at these two pictures, so one is an airship, the first one, and the second one is a commercial airliner. Now look at the relative sizes of the fin with respect to either its envelope or the fuselage. You see that there is quite a bit of mismatch. Now what you notice is undersized fins. Now it is undersized for many different reasons. It being the location and the weight of the fins that you can put there. Now, airship is very delicately balanced, so you cannot put very large fins at the back, so which would make it tail heavy, and then the airship would always be nose up. Then there is the issue of ground handling. If it is too big, it becomes very difficult for the ground handling crew to handle the aircraft when it is on the ground. Also, the hangar size, and most importantly, these fins, they have to be mounted on a balloon that is an envelope. So that is another challenge structurally. So because of all these reasons, you cannot actually have a fin which can stabilize the airship. Now, as a penalty, what we have is that a steady rate of turn. That is basically the airship would turn away from the wind direction, not towards it, as we require it to be stable. So this is the key reason why airships are directionally unstable. Now, let's address these issues with some of the mechanical effects that we can do. So I did this as a part of my PhD work. So this was the airship that was constructed with the methodology that was developed. Now the methodology involved framing optimization problem and then testing it for validation in a wind tunnel setup. So this was that setup, and with that we were able to size a fin which would not make it directionally stable, but at least minimize the instability in the system. So that's what we were able to achieve and prove as well. Uh, Across the world, there are many different approaches towards addressing this. So, for example, some institutions, they went with lenticular shape, which looks like a flying saucer now. And this is one of the ways that they thought of doing this. Although there is a drag penalty when we talk about these kinds of systems, and then we have the famous airlander, which is basically multi-load system. So you put two or three airship hulls together, and you rely on both the static lift, that is the buoyancy, and the aerodynamic lift here. And then we have a different hybrid configuration, which basically merges the fixed wing and the airship together. So moving on. So now let's get to the autonomous control bit. Now, this is what the control architecture typically would look for any unmanned system, not just for airships. Now, this is how I had designed it for airships as well. Now, I know this looks a little bit scary because there are a lot of things happening here. So I'll address each of them block by block. So let's start with the airship block, which is at the bottommost. So airship block is nothing but the physics of the system. So in our case here, it's the airship. So how would the airship behave when you apply a certain control input or when there is a presence of wind? So that is what airship dynamics captures. And it could be either a real system, if you're flying it on an actual system, or it could be a simulated platform. So in my case, I used both of them. So this is one of the simulations that was done on the Gazebo platform. So here you see control inputs are applied and the airship basically takes off and then just moves ahead. So you can see that it has VTOL capabilities. And as you can see, there is no control implemented, and that's why you are seeing that oscillation in the airship. So moving ahead, so that makes the first component, that is the airship. The next component that we have is the control inputs, that is basically the input that the users would give to control the airship. Then, of course, there is some disturbances which is going to come from the environment. And then we have estimators. Now, what is this estimator? It's nothing but, since we have a lot of onboard sensors, to make some useful information out of it, we need estimators. So this basically filters out a lot of noise in the measurement. It estimates several states which are not directly obtained from the sensors, which is basically indirectly obtained using a model. So you estimate several things like position coordinates, that's the where exactly the airship is in 3D space. Then you have the speed, airspeed, the wind direction and the speed of it, the attitude, which is the roll pitch and yaw angles, the velocities and the acceleration of the system. So that's what the estimator would do for you. And once you have those values, we have the first layer of control, that is the autopilot. Now, what autopilot does is it takes the airspeed, altitude, and heading inputs, and then it generates appropriate control inputs by looking at the feedback. So feedback is obtained from the estimator as to what exactly the airship is doing, and then the autopilot would make sure that that is being done. So it's as I mentioned, a low-level controller, and this is the one that would directly control the control surfaces and the propulsion systems. So the main key function is to stabilize the airship and to maintain and regulate whatever input is given from the higher up, either user or a control block. So it would basically control things like airspeed, altitude, attitude, and course heading angle. So this basically gives us a sense of where and in general direction in which airship should be moving, what is the speed at which it should be operating. So that is what autopilot would ensure. Then the next layer up, we have okay, so this is an implementation of a control autopilot system. So here we use the mobile operated autopilot. So you see that in this, there is not a lot of oscillation, and you basically see that it's able to hover in one place for longer durations. Maybe I just skip through this quickly. Yeah. So the next layer of control we have is tracking. So this is basically, we have a path defined for the tracker, and it would ensure that it would basically follow that path. And the way it does it, it generates this airspeed, altitude, and heading inputs for the autopilot. So this is what happens here. So let's say we want to follow the red line, but it may not, the airship is physically not able to follow that. Maybe the dynamics of the system doesn't allow it. Maybe there are certain environmental factors like wind, which is not allowing the airship to follow that red line. So that is when the airship would require some kind of a planned trajectory, which is feasible and is also close to the actual desired trajectory. So that is what this would do basically. It would take into consideration the dynamics and then make the airship follow that particular path. And the next one that we have is the manager. So the path manager is basically what we have is, let's say we have several GPS locations or waypoints. The manager would basically make a path out of it. Here also, the airship would consider, the manager would consider the dynamics of the system, and then it generates a smooth, feasible path for the airship to follow. And this becomes the output of the manager, becomes the input to the tracking controller. That is the path definition. Again, so the final layer of control that we have is the planner. So planner is on top of all of these layers of control. And what planner would do is basically generate the waypoint itself. Maybe you could have collision avoidance. If you want to operate this in an urban terrain, there would be a map of the urban locality, the basically where there are buildings, what is the point that the airship needs to avoid, and that is how it would generate waypoints. It could also have terrain map, as in like if there are some mountains to be maneuvered across. So things like that would happen in the planner. And this is where there is a potentially artificial intelligence and machine learning play a very good important role in the planner part of the entire autonomous structure. So putting it all together, what we have is the total autonomous architecture for the airship. And also not to forget is the green lines, which is the interface. So you need to be able to communicate between each of these blocks. And typically, we use ROS for this, robot operating system. It could be used, it can be tailored for different applications, but there are many different ways of doing it as well. So yeah, with that, thank you for the listening to me very patiently. I would be happy to answer any questions if there are any.